Well, thanks for joining me. We're going to go through the stoichiometry quiz, and hopefully after you watch and see how all the problems are worked out, you'll have a much better idea about what maybe mistakes you made. All right, these aren't in any real order. Yours may have been slightly different, and I'll just kind of go through as quickly as we can here. So this one says you take some nitrogen gas and hydrogen gas and you combine it, and we're going to make some ammonia from that. And so the question says here, how many grams of nitrogen would be needed to produce 3.18 grams of ammonia? Now, if we were doing the little map, we can put that on here. We're starting off information about ammonia, and we are going to, our unknown information is about nitrogen. We are starting at mass mountain up here, and we're going to mass mountain over here. So this should be a three-step conversion, going from grams of ammonia to moles of ammonia, then using the coefficients from the balanced equation to go moles of ammonia to moles of nitrogen, and then finally moles of nitrogen to grams of nitrogen. So the way I like to see these set up is write always what you're looking for. X grams of nitrogen equal to 3.18 grams of ammonia. So your first step is to figure out what one N and three H's weigh. Well, nitrogen weighs 14, and each of the three hydrogens weighs 1. So that's 17 grams of ammonia per 1 mole of ammonia. And grams of ammonia cancel like that. The second step here is to cross the middle bridge. And to cross the middle bridge, we always use coefficients from the balanced chemical equation. There's an understood 1 here and a 2 here. So we want the units to cancel out. So in the denominator, 2 moles of ammonia, and in the numerator, 1 mole of nitrogen. And moles of ammonia cancel. If we stop now, we'd be right here at moles of nitrogen, and where we want to get to is 2 grams of nitrogen. So we need one more step. Nitrogen is element 7, but because it's diatomic, it weighs 14 grams per mole. So 1 mole of nitrogen gas is 14 grams of nitrogen N2, and moles of N2 cancel. Go ahead and type that all in your calculator, and you should get an answer of 2.62 grams of nitrogen. All right, let's keep moving. We're going to keep going through these as quickly as we can. For the next one, we're dealing with this reaction that says aluminum sulfate plus barium chloride goes to aluminum chloride plus barium sulfate. How many grams of barium chloride, that's this stuff right here, how many grams of barium chloride will react with 188 grams of aluminum sulfate? Well, hopefully you remember that if we're doing our little map here, the little dirty birdie feet map, we are starting with information about aluminum sulfate, specifically the mass, and we are trying to get information about barium chloride, the mass, up here. So that's a three-step conversion, grams of aluminum sulfate to moles of aluminum sulfate. Use the coefficients of the balanced chemical equation to go from moles of aluminum sulfate to moles of barium chloride, and finally moles of barium chloride to grams. Now, for both of these, we're going to have to figure out the molar mass. So I'm going to go ahead and do that right now. So I notice that I have, on aluminum sulfate, I have 2 aluminums, and they each weigh 27 grams per mole. So that's 54 grams. I have 3 sulfurs total. They each weigh 32 grams. That's 96. And I have 12 oxygens, and they each weigh 16 grams, and that's 192 grams. So the total for that is 342 grams. That's what Al2SO43 weighs. And while I'm at it, I might as well go ahead and do my barium chloride. So in barium chloride, I have 1 barium, and it weighs approximately 137 grams per mole. And I have 2 chlorines, and they each weigh 35 63.5 grams for 71 grams. For some reason, it's not letting me put that in there. There we go. All right, and that gives me a total of 208 grams for barium chloride, because I'm going to need that information. Now, let's go ahead and solve this thing. So, we're trying to figure out here how many grams of barium chloride are equal to 188 grams of aluminum sulfate. Now, our first conversion is going to be to go from grams of aluminum sulfate down to moles of aluminum sulfate. And we just came up with this relationship right here, that every 342 grams of aluminum sulfate is equivalent to 1 mole of aluminum sulfate. Grams of aluminum sulfate cancel, like that. Our next step is to cross the middle bridge using the coefficients from the balanced chemical equation. There's an understood 1 mole of aluminum sulfate reacts with 3 moles of barium chloride. Be careful to make sure the units cancel. 1 mole of aluminum sulfate will react with 3 moles of barium chloride. Moles of aluminum chloride cancel like that. And finally, the last step is to go from moles to mass of barium chloride. And we took the time earlier to figure out that 1 mole of barium chloride weighs 208 grams. 1 mole of barium chloride weighs 208 grams. Moles of barium chloride cancel. And if you take the time to go 188 times 3 times 208 divided by 342, you should get the right answer of 114 grams of barium chloride. Okay? All right. 2 down, 8 to go. This next one, we have to come up with the equation. So it says copper 2 oxide. Now remember, copper 2 means copper is 2 plus, and oxygen is always a 2 minus in a binary compound. So this stuff is CuO. That's copper 2 oxide, and it's going to decompose into solid copper plus oxygen. Remember, oxygen is always diatomic. Next, we have to balance that equation. We have 2 oxygens on the product side and only 1 on the reactant. Therefore, we need a coefficient 2 in front of both the copper 2 oxide and the copper. Now we have a balanced equation. So it says if we start with 95.4 grams of copper 2 oxide, how many grams of copper will we get and how much oxygen? Now, if you only solve for one of these, either the copper or the oxygen, you're really done because you know the rest of it must be the other material. So let's set this up. So I'm going to just arbitrarily pick the copper. How many grams of copper would I get from 95.4 grams of copper 2 oxide? That's the question. Now, this is a gram to gram, 3 steps. I'm not going to go through the setup. I think we understand that. So the first thing I have to do is figure out what 1 Cu and 1 O weigh. Well, copper weighs 63.5 grams per mole. And the oxygen weighs 16 grams per mole. So that means the molar mass of that must be 79.5 grams. So every 79.5 grams of CuO is 1 mole of, right thing here, of CuO. Okay? Now, we don't use the coefficient 2 in that first step because we're just doing 1 mole of it. Now, as we cross the middle bridge, as we go from one substance to the other, that's when we use the coefficients. So 2 moles of CuO, 2 moles of Cu. 2 moles of copper 2 oxide will produce 2 moles of copper. Let's see if we go back. Here we go. Of copper. Moles of CuO cancel like that. And finally, my last step is to figure out what 1 mole of copper weighs. And I should know that. 1 mole of copper, 63.5 grams, because I just wrote it right over here. And moles of copper cancel. Now, if you do the math there, you're going to get 76.2 grams of copper. But the question says how many grams of copper and oxygen? Well, if we think about it, we started with 95.4 grams of copper oxide, copper 2 oxide. And if we subtracted the 76.2 grams that was copper, the number we have left is 19.2 grams. That must be the oxygen. So the answers we're looking for on that one, there were two. You would have said 76.2 grams of copper and 19.2 grams of oxygen. All right, let's keep moving. This one deals with an automobile airbag, and we start with 125 grams of this material called sodium azide, and we want to know what volume of nitrogen gas would be produced. Now, if we want, we can draw a little map just so we know where we're at here. We're starting off with information about sodium azide, NaN₃, and it is a mass, so that's right up here. And we're going to find information about nitrogen. We must be assuming it is at STP, and that's a volume of a gas over here. So this will be a three-step problem, so let's go ahead and get started right away. How many liters of nitrogen, what we're looking for, equal to what are we given? 125 grams of sodium azide. Now, I will assume you can figure out 1 sodium weighs 23 grams and 3 nitrogen each weigh 14 for a total mass of 65 grams of NaN₃ per 1 mole of NaN₃. That's the molar mass of sodium azide. That's our first step. The second step is always to use coefficients from the balanced chemical equation to go from moles to moles. 2 moles of sodium azide, 3 moles of nitrogen. So I put on the bottom 2 moles of sodium azide, 3 moles of nitrogen. Moles of sodium azide cancel. Now, I'm almost done. One more step. I'm not interested in moles of nitrogen gas, but liters. And if you remember the gray box in the room, 1 mole of any gas at STP occupies 22.4 liters. Typing in all those numbers on my calculator, what I should get is an answer of about 64.6 liters of nitrogen gas. Now, I'm not concerned about sig figs on that one. If you wrote 65 liters, that would have been okay as well. All right, let's try the next one. Okay, on this one, we're dealing with calcium and oxygen in a synthesis reaction making calcium oxide. So we want to know how many grams of oxygen must be used so that we can get 6.85 grams of calcium oxide. So if we're going gram to gram, that's a three-step problem. We've seen this problem many times before. X grams of oxygen, what we're looking for, equal to 6.85 grams of CaO. My first step, and I'm not going to show it, but I'll just mention it, calcium weighs 40 grams per mole and oxygen weighs 16. So 40 plus 16 is 56 grams of CaO is 1 mole of CaO. That's the first step. The second step is to use the coefficients from the balanced chemical equation to go from one substance to the other. So 1 mole of O2, 2 moles of CaO. So every 2 moles of CaO that are produced requires 1 mole of oxygen. That's that step, like that. Now, what we're interested in is not moles of oxygen, but mass of oxygen. Now, you have to remember, O2 is diatomic. So what does 1 mole of O2 weigh? Not 16, but 32 grams of O2. And moles of O2 cancel. Typing that all into your calculator, you should get an answer of 1.9 0.96 grams of oxygen for a final answer. All right, 15 minutes in, we're about halfway done. We're doing pretty good on time, I think. Let's try this one. So we're looking at this big long combustion reaction. You've got a combustion of a hydrocarbon, C₄H₁ plus 13 O₂ goes to 8 CO2 and 10 water. Now, I don't like this question. I'm going to tweak it. I'm going to show you what you should have done, and then show you what the author of the question did, and then how I would change it. The author of the question said the answer was, I believe, 2 liters. Now, here's what they did. They simply said, if you have 10 liters of hydrogen, and how many liters of propane would you start with? X liters. And they really simply, is that what they did? Let's see, there's 10 liters of water, yeah. So if this is what they did, they simply said, well, 2 is to 10, or 2 is to 10 is 1/5, so 1/5 of 10 is 2 liters. So they put the answer as 2 liters. Now remember, you cannot use liters and just cancel that way, okay? Now, it would actually work math-wise if we allowed ourselves to do this, and I'm going to show you what's wrong with it in a second. If we said X liters of C₄H₁ is equal to 10 liters of water, you could say, well, 22.4 liters of water is 1 mole of water. Then using the coefficients, 10 moles of water, 2 moles C₄H₁, and then finally 1 mole C₄H₁ is 22.4 liters of C₄H₁. Now, if you did this, and there's several mistakes with this, the 22.4 liters cancels, and so we really just have 10 times 2, 20, divided by 10 comes out 2 liters of C₄H₁. We really shouldn't be doing this because, quite frankly, water is not a gas at STP, so we can't even use this first step at all. Now, if I were doing the question, I would have made it maybe if we have 8 liters of CO2, what volume of C₄H₁ do we start with? And then it would look very, very similar. It would just say 8 liters of CO2 here, and then it'd be, say, 22.4 liters of CO2 is 1 molar of CO2, and then it would say 8 moles of CO2 is 2 moles of C₄H₁, and 1 mole is 22.4 liters, and we get 2 liters. That would have been an okay question. All right. Now, the way the question was asked, if you wanted to get an answer, and I'm just going to show you what you would have had to do, and it's way more complicated than what I would have wanted you to really do on this question, is this. How many liters of C₄H₁ is equal to 10 liters of water? What you'd have to do is say, well, in 1 liter of water, there are 1,000 milliliters of water, and the density of water is 1 milliliter is 1 gram. Then you would go, well, every 18 grams of water is 1 mole of water. Now, all of that just to get us to grams, right? And then from here, then the question would look somewhat similar to what we've done in the past. Every 10 moles of water would be equal to 2 moles of C₄H₁. And then finally, because what we're really being asked about is volume of C₄H₁, and we're assuming it's STP, we would say 1 mole of C₄H₁ is 22.4 liters of C₄H₁. Now, if you took the time to do that, you would have got an answer of 2,489 liters of C₄H₁. That was the closest answer to 2 liters that was a choice. And some of you maybe did all that and got that answer. Good for you, okay? Again, these were author-made questions, and it was my fault. I didn't look at them more carefully before I assigned them. I assumed that they would be error-free, but they were not. All right, let's try another one. All right, on this guy here, we have 4.31 liters of A, and we are trying to figure out how much D we're going to get in terms of volume. Now, some of you didn't like this question because it didn't have like compounds. It's just using the letters A, B, C, D. Well, look, we can still solve it. We're starting with substance L, and we're starting at volume, and we're going to substance A, and we're going to volume. So this should be a three-step problem. So let's work it out. How many liters of D are equal to 4.31 liters of A? And our first step would be to say, well, any substance, 22.4 liters of A, would be 1 mole of A. That's the first step. The next one, that middle conversion using the coefficients, how about 2 moles of A will produce 6 moles of D. And finally, that's the middle step. Finally now, we're going to say, well, every 1 mole of D is 22.4 liters. It's still a gas. Notice that the 22.4s cancel, so it's really just 4.31 times 6 divided by 2. And that gives me an answer of, it might be 12.93 in your calculator, but based on sig figs, it would be 12.9 liters of D. Because we have 3 sig figs in the number 4.31, we're going to keep 3 sig figs. Again, this is one of the ones where if you put 12.9 or 12.93, I wasn't going to mark that one wrong for you. Next, we have sodium and nitrogen gas combining to make sodium azide. So if you were to start with, let's say 35.6 liters of nitrogen gas, we want to know how much in mass of sodium azide that might produce. So let's go ahead and set this up. So we're looking for X grams of Na₃N are equal to 35.6 liters of nitrogen gas. Now, we're going from, if we wanted to draw the map, that helps us. We're starting at at nitrogen, and we're at Leader Lagoon, and we're going to sodium azide, and that is going to be Mass Mountain up here. So it's a three-step problem. So our first step is to convert liters into moles. Well, every 22.4 liters of any gas at STP will be equivalent to 1 mole of that gas, and liters cancel like that. Now we use the coefficients from the balanced chemical equation, 2 moles of sodium azide from an understood 1 mole of N₂. So every 1 mole of nitrogen will produce 2 moles of NaN₃. Moles of nitrogen cancel. And finally, almost done, we need to get that into mass. Now, you have here I wrote NaN₃. I think we want to write Na₃N. Na₃N. There we go. And so Na₃N, you got 3 NAs at 23, which is 69 grams, and you have 1 nitrogen at 14 grams. So how about 83 grams per mole? Does that sound right? It does to me. So 1 mole of Na₃N is 83 grams of Na₃N. And moles of the sodium azide cancel, and we're left with our final answer there being 264 grams of Na₃N. This is another one of the sig fig ones. If you put 263.8, and it marked it wrong, I would definitely give you that. 35.6 has 3 sig figs, which means our final answer should have 3 sig figs, 264. All right, let's try this one. we have 4 HCl plus O2 goes to 2 chlorine and water. So we want to calculate the volume, X liters, of HCl if we start with 1.56 liters of oxygen. So a liter to liter should definitely be a 3-step conversion. So here we go. How many liters of HCl is equal to 1.56 liters of O2? Now, some of you might just say, well, isn't it just going to be 4 times more? Well, yes, you're correct. It would work out that way, but let's go ahead and set this up. So we know that every 22.4 liters of O2 is 1 mole of O2. Liters cancel. Now we go to the coefficients from the balanced chemical equation. 4 moles of HCl, 1 mole of O2. 1 mole of O2, 4 moles of HCl. Moles of O2 cancel. And finally, let's bring this one to a completion here. How about 1 mole of HCl? If it's at STP, 22.4 liters of HCl. Moles of HCl cancel. Now, collaterally, we got rid of a 22.4 down here and up here, so really it's just 1.56 times 4, and that gives me the answer here of 6.24 liters. That should be your answer for that guy there. All right, we're getting near the end here. All right, let's try this guy here. Now this was a toughie. This was actually a limiting reactant one, and maybe we're gonna work this one a couple different ways here. Okay, you got here C₃H₁ plus O2 goes to CO2 plus water. Now, in this problem, we want to balance it. So we do the carbons first, put a 3 here, do the hydrogens next, a 4 here, and finally do oxygens last, put a 5 here. So we're starting with 188 grams here and 185 liters here. And we want to know how many molecules we'll get here. Now, I'm going to do this one a little bit different. You could work the problem starting with 188 grams of propane. And if you did that, if you go from here to here, you are going to get for an answer, if you do that, 1.03 times 10 to the 25th molecules of water. If instead you go from 185 liters and figure this out, you will get an answer there of 3.98 times 10 to the 24th molecules of water. And the correct answer is always going to be the smaller of the two. Now, I will assume you can do liter to molecule and gram to molecule question. We will do one of those, but I want to show this to you from the perspective of limiting reactant, how maybe we would have done it after Friday's class, all right? So we'll get rid of that. We'll get rid of all this here. All right. Now, what we said is whatever I give you, convert to moles. So we're going to do this kind of that expanded way, right? The exploded view. So C₃H₁ has a molar mass. When you do 3 carbons times 12, it's 36, plus 8 more from the hydrogen, 44 grams. So if I divide this by 44 grams per mole, unfortunately, I don't have a calculator near me. That's really quite unfortunate. But let's keep moving. And then over here, I'm going to divide this one by 22.4 liters. I want to see if I can just pause this thing for a second. All right, so I found my calculator. 188 divided by 44 means that I have 4.27 moles of C₃H₁. This is what I have. Now, when I do the 185 liters of oxygen and I divide that by 22.4, so 185 divided by 22.4, I get an answer of 8.26 moles. Let's try again. Some technical issues here. Try one more time. 8.26 moles. Because this is 22.4 liters per mole. All right. The next thing we said is we could either figure out what we need, and maybe we'll talk about that, or maybe I'll just show you the other way to do it. Then we said, you know, if you're not doing the thinking method, just divide by the coefficient. So divide this by 1, and you get the number 4.27. Divide this one by the number 5, the coefficient. So 8.26 divided by 5 comes out 1.65. Then we said, based on these two numbers, the smaller number is the limiting reaction. Okay, so look at these two numbers. 1.65 is smaller. And what that says is that the oxygen is the limiting reactant and the propane is in excess. So now the only important number for us is this number right here, the 8.26 moles of oxygen. So based on that, I can figure out the molecules of water. So how many molecules of water are equal to 8.26 moles of oxygen? And here's what I do first. I use the coefficients. 5 moles of oxygen will produce 4 moles of water. Moles cancel. Now, I'm not interested in moles. I want molecules. So now I need to do one more step. 1 mole of water is 6.02 times 10 to the 23rd molecules of water, and moles of water cancel. Now, if I took 8.26 times 4 times Avogadro's number divided by 5, and I don't have a calculator in front of me, but I know what I should get for an answer. I should get the answer 3.98 times 10 to the 24th molecules. Okay, and that should be the answer, this is of water, of what we should have gotten for that one. Now again, that one, you know, you could have solved it by simply working the problem twice and picking the smaller answer, right? I'll just do it very quickly for those of you that would want to see that, right? If we would have said how many molecules of water are equal to 188 grams of C₃H8, our first step would have been to say, well, C₃H8 is 44 grams per 1 mole of C₃H8. Then we would have used the coefficients, 1 mole C₃H8, 4 moles of water, and then finally 1 mole of water, 6.02 times 10 to the 23rd molecules of water. And that would have given me a number 1.03 times 10 to the 25th molecules of water. Now, if I would have started with the oxygen instead, I would have said, and it would have looked very similar, right? We'll do it in a different color. We would have said X molecules of water equal 185 liters of oxygen. Our first step would be 22.4 liters of oxygen is 1 mole. And that would have, if I stopped, given me the 8.26 moles. And then from here, everything is the same as what I did right up here. But I'll go ahead and put it in nevertheless. 5 moles of oxygen, 4 moles of water from the balanced coefficients. And finally, 1 mole of water, 6.02 times 10 to the 23rd molecules of water. And that will give you 3.98 times 10 to the 24th molecules of water. Because the second number, this one right here in red, is smaller than this one, the smaller one is the one that wins. It's the one that we run out of material from first. All right, that, ladies and gentlemen, was the quiz. It was actually much harder than I had anticipated it would be for you guys. It was not my intent. I didn't do my due diligence and look at the questions thoroughly enough before I gave it to you. So I'll try to do better on my end. All right, I hope this helps you a little bit to understand maybe what you did wrong on that quiz. All right, take care. Have a good weekend. Bye-bye.